All right, I'm going to talk about CarrierSenseMultipleAccess protocols, or CSMA protocols. I'm going to refer back to Aloha real quick. And one good thing about Aloha is it's able to maximize throughput over long distances. But in the case of local networks or LANs, we can find a better solution to the problem. And in this case, that's CarrierSense protocols. And the reason that is because Aloha just says goodbye to all the data. It doesn't matter, like, it doesn't care if it gets there, unless there's a collision, and it'll just resend it again. But on the local settings, they're able to check for signals in the lines that they're communicating with. And that's like an analog process because it's going to be, different from what they're outputting. The first one is persistent CSMA, and it listens to the channel before it transmits only if the channel is idle. So, like, if it starts right off the bat, like, it has a probability of 1 that it's going to send out that that's the data. So, but that ends up being a little bit inefficient because collisions can occur this way. Like, if they detect that the lines are busy, they just wait immediately. It's like they're next in line, and they just jump at the bat to go off. And in that sense, like, 2 stations can be waiting to broadcast, and when that happens, a collision occurs. So it's not as efficient a way to solve the problem, but it does outperform Aloha in terms of throughput because less collisions occur as a result. So it doesn't completely eliminate the problem, but it does help to solve and make it a little bit more efficient in terms of throughput. It relies on the bandwidth delay product, which the earlier presentation referred to, and I'm just going to say that that refers to the number of frames that fit on a channel at any given time. And in terms of LANs, these products tend to be smaller. So that's one of the reasons why less collisions occur, because they're not occupying as much space on the line. So by the time they send a signal, it may not, the window for them to seize the channel is going to be significantly less. And the next one is going to be a non-persistent CSMA. And like the first one was persistent with a probability of 1 that'll send. This one, it's just kind of, it checks to see if the line's busy. And if it's not, it's going to send. But if it is, it's just going to wait a random period of time and come back later and try to do it again. So in terms of maximum throughput, it does reduce the collisions, but the delay between your requests are significantly increased, and that's one of the trade-offs between this and one persistent CSMA. It does have a higher channel utilization though, and it just means that there's less downtime on the channel, but the delays once again are bigger. Now, the real interesting part about the P-persistent CSMA, it kind of takes a hybrid approach to the two. While the first one was transmitting with a probability of 1, this one transmits with a probability of P, and that can be user allocated as I show you later on. But it attempts to send a packet, and if the channel's idle, it'll send it. But if not, when it's busy, it'll just have a small percentage chance of sending immediately after that channel becomes idle, or it will delay itself and wait for another slot and then send itself again. So it's kind of yielding to somebody in line with it, and it's being a little bit of a gentleman. But the strange thing about that though is it can wait persistently until it times out, so to speak, and then it'll just reapply that same process. So it's going to be, it does maximize throughput, and it does end up reducing collisions a significant amount. The 3 CSMAs versus the Alohas, as I said before, if we look up here, we can see that's going to be a P persistent, and it's going to be transmitting if the channel is idle with a probability of 0.01. And while that seems kind of low, it's just giving itself the chance to avoid a collision based on, it seems kind of random, but it ends up doing a good job about it. And then if there is a collision, it just ends up backing off and reapplying the algorithm. And we see that it outperforms significantly with the maximum throughput closer to 1. That's down here when we look at slotted Aloha, that's maxing out at a 37% chance to 37% throughput, but we see it gets close to 100. And the non-persistent CSMA, it falls in between. It's still very efficient in terms of reducing collisions, but they're all still they still occur. If we look forward to since the collisions are kind of an inevitability, they started to implement CSMA with collision detection, and like the other CSMAs, they check the channel first to see if they're broadcasting, and the way it decides whether or not to go, it's outputting a specific signal, and if they hear a different signal, within a given amount of time, they know that a collision is occurring, and they'll just back off and yield the line for somebody else, or until it's idle and then go themselves. It is the basis of the classic Ethernet LAN, so it's something that's very prevalent, and right now they use a modified version of this, a little bit more efficient. And as I said, the collision detection process is analog. That just is determined over electrical signals over the wire. If you look down at the graph, these are contention slots. With Aloha, it's a slotted system, and in the contention period, if say a collision is occurred, they back off, and then the next person who gets the line towards the end of the collision period seizes the line, and everybody else knows that somebody's going to be broadcasting over that channel. One of the awesome parts about it, though, is that it's kind of strange that whenever they're contending for spots, they have to have a given amount of time, and we would think that it would be if it took 5 seconds to do a round trip over to communicate with the machine and get a response, but that's not the case, because that would create more collisions than it would be fixing. So it actually has to be double the time interval as it would be. Say t is equal to 5 seconds for a request and a response, it would be 2t in order to reduce the collisions and allow somebody to seize the channel.